At the coldest shore of our solar system, there is a fever glowing in the dark. You would expect the farthest place from the sun to be the most frozen thing we know, not a place that acts like the rim of a furnace. Stay with me, because this strange heat is real, measured, and far more important than it first sounds. But first, subscribe if you want big space stories translated into plain English before the next surprise drifts into your feed. For a long time, most people pictured the edge of the solar system like the edge of a map. You go far enough, the sunlight thins out, the cold takes over, and everything becomes quiet, simple, dead. That picture feels right in your bones. The farther you walk from a campfire, the colder your hands get. So how could the last border of the sun's domain be heating up instead of fading away? What makes this story so gripping is that the answer did not come from a shiny new machine. It came from two old spacecraft launched in 1977, when disco was on the radio and nobody had ever seen the planets up close. Voyager 1 and Voyager 2 were built for a mission that was supposed to feel huge at the time, then end. Instead, they kept going. Decade after decade, they drifted into a place no one on Earth had ever touched. And out there, beyond Pluto, beyond the neat schoolbook picture of the planets, they found something that sounded almost wrong. The skin of the sun's giant bubble was not calm. It was compressed, stirred, bent, leaking, and in places hotter than scientists had expected. Not hot the way a cast iron pan glows on a stove. Hot the way a ghostly gas can be hot, with particles moving fast in a place so thin you could hardly call it air at all. Now let us start from the beginning. The first thing to fix is a common mistake. People say, the edge of the solar system, as if there is one clean border, like the edge of a dinner plate. That is not true. The solar system has planets, comets, and icy bodies far out in the dark, but the sun also makes a much larger bubble around all of them. That bubble is called the heliosphere, which simply means the sun's sphere of influence, built by the solar wind, a constant stream of charged particles blowing outward from the sun. So when scientists talk about the heating edge, they are not saying Neptune is suddenly toasting. They mean the boundary region where the solar wind runs into the thin gas between the stars. Think of a boat pushing through water. The water piles up near the front, waves curl, pressure changes. The neat line you imagine becomes a messy, moving zone. The edge of the sun's bubble behaves more like that than like a wall. Early on, this outer region did not get much love. It sounded cold, empty, and far away. Even the spacecraft that would later transform it were underestimated. Voyager was built in another age, with old computers, tiny memories, and power supplies that slowly fade as plutonium decays. Yet these two stubborn machines became the only things humanity has ever sent into interstellar space, the space between stars. The underdog in this story is not just a place, it is the mission that refused to die. Before the Voyagers reached the boundary, scientists had models, smart guesses, and a lot of missing pieces. They knew the solar wind leaves the sun at around 1,000,000 miles per hour. They knew it cannot keep that pace forever. Far from the sun, that wind crashes into the material outside our bubble and slows down. Somewhere out there, it crosses a shock, a rough slowing point, then pushes through a turbulent outer zone called the heliosheath, before finally meeting the true border called the heliopause. The first surprise was not even the heat, it was the fact that the edge was more alive than expected. Back in 2004, Voyager 1 crossed the termination shock, that slowing region, at about 94 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, so that is 94 Earth-to-sun gaps lined up in a row. Voyager 2 crossed its own shock in 2007, but at about 84 astronomical units. Same solar bubble, different distance. Right away, the border was telling us it was not neat or even. Scientists expected the shock to behave almost like a traffic jam in space. The solar wind would rush out, hit resistance, bunch up, and follow the script. What they actually saw was stranger. According to NASA's Jet Propulsion Laboratory, the wind slowed more than expected, and sometimes it even seemed to flow back inward toward the sun. Imagine turning on a leaf blower and watching some of the stream curl back at you. That was the mood out there. Edward Stone, the longtime Voyager project scientist at Caltech, helped frame how weird this really was. The sun's interaction with the matter between stars was proving more dynamic and complex than scientists had imagined. Even the magnetic field changed its rhythm. Before the shock, the field switched direction in a regular pattern as the sun rotated. After the shock, that pattern stretched out. What should have passed like stripes on a moving belt lingered far longer, as if the whole outer bubble had turned sluggish and sticky. The second finding changed everything. Scientists had expected one class of high-energy particles, the particles that can become cosmic rays, to peak right at the shock. That would have fit the old idea. The boundary would act like a perfect accelerator. But Voyager 1 did not find that peak where it was supposed to be. Instead, the intensity kept rising as the craft moved farther out. In plain language, the strongest action was not where the script said it should be. The engine room of the Surprise seemed to be somewhere else. That mattered because it meant the edge was not just a line, it was a system. A layered, moving, badly behaved system. The outer solar bubble was holding energy in ways scientists had not pinned down. Like opening your freezer and finding not one cold shelf, but a hidden warm draft in the back corner. The result forced a change in the whole picture. The farther Voyager went, the less the old map worked. If before this story you pictured the solar system ending in a clean, frozen shell, what picture do you have now? Tell me in the comments, because your answers help me see which big ideas need the clearest explanations next. Then came the crossing everyone had waited for. On August 25, 2012, Voyager 1 reached interstellar space. On November 5, 2018, Voyager 2 did the same. NASA described Voyager 2's crossing as happening about 11 billion miles from Earth, or 18 billion kilometers. Light, moving at the fastest speed nature allows, takes about 16.5 hours to get from Voyager 2 back to us. If the sun were a porch light across the street, Voyager was no longer even in the neighborhood. Scientists expected the plasma outside the heliosphere to be colder than the plasma inside. Plasma is a hot gas made of charged particles. That basic expectation turned out to be true. But when Voyager 2 measured the plasma just outside the heliopause, it found something else too. The plasma there was slightly warmer than expected. Not a little bookkeeping error, warmer enough to matter, warmer enough to suggest the boundary was being compressed. This is where the headline about heating up begins to make sense. According to the 2019 Nature Astronomy papers on Voyager 2's crossing, the temperature in that nearby interstellar plasma came in around 30,000 to 50,000 Kelvin, while many models and earlier expectations pointed lower, around 15,000 to 30,000 Kelvin. Those are huge numbers, but do not picture a blowtorch. The gas is so thin that it would not feel like stepping into an oven. It is more like measuring how fast the few particles there are happen to be darting around. Still, the difference was real. Scientists expected cold. They found colder than the inner heliosphere, yes, but warmer than the models had said. Compressor gas, and it can heat. That is true in a bicycle pump, true in an engine, and true in strange ways at the border between our star and the galaxy. The edge was not just sitting there, it was being squeezed, shaped, and stirred. Voyager 2 also saw a slight rise in plasma density just before it exited the heliosphere. More particles packed into the same space. Outside, the plasma was denser than inside, just as expected. But the picture on both sides of the boundary suggested compression, like fabric bunching at a seam. Scientists could see the seam. They could measure the bunching. What they could not fully explain was why the seam behaved exactly that way on both sides. And that is one of the smartest parts of this story. Scientists did not say, "Mystery solved, good night." They said something better. They said the data confirm a strange effect, and the cause is not fully understood yet. That kind of honesty matters. It turns discovery from magic back into science. The most exciting space stories are often the ones where the measurements are solid and the explanation is still catching up. The third discovery puzzled scientists in a different way. The magnetic field just beyond the heliopause turned out to be almost parallel to the magnetic field inside the heliosphere. Voyager 1 had hinted at this first. Voyager 2 confirmed it. Scientists had only one sample with Voyager 1, so they could not tell if that odd alignment was a fluke. But when Voyager 2 found it too, the results started looking like a real property of the boundary itself.
Why is that strange?
because many people expected a sharper turn, almost like crossing from one weather system into another. You walk from warm air into cold air, and the wind can shift. You step from one side of a riverbank to another, and the slope changes. But here, the magnetic fields on both sides looked more lined up than expected. It was as if the outside wind had draped itself along the skin of the sun's bubble instead of colliding head-on and scrambling everything. NASA also reported that the heliopause may be leaky. One Voyager instrument saw a trickle of particles from inside the heliosphere slipping through the boundary into interstellar space. That sounds small, but it changes the feeling of the whole border. Instead of a sealed snow globe, we may live inside something more like a tent in a hard wind, stretched tight but not perfectly closed. Some regions also seem more porous than others. Voyager 2, which crossed closer to the flank than the front, may have passed through a leakier neighborhood. If stories like this make the universe feel less abstract and more real, would you like the video and tell me why below? That signal helps YouTube notice that careful science stories are worth showing to more people. Now the scale starts swinging in a way that almost feels unfair to the human brain. One minute we are talking about tiny charged particles and slight rises in density. The next minute we are talking about a bubble carved by the sun that stretches far beyond the planets. That jump in scale is not a side detail. It is the heart of why this discovery hits so hard. Your refrigerator hums in a kitchen corner. The heliosphere hums across distances so wide that a solar wind gust can take about a year just to reach the edge. And then comes IBEX, the Interstellar Boundary Explorer. Unlike Voyager, IBEX does not go to the edge. It stays much closer to home and maps the boundary by detecting energetic neutral atoms, tiny fast particles that come back from that distant region. David McComas of Princeton University led this work, and the mission did something that sounds almost impossible at first. It used faint returning particles to sketch the shape and motion of a frontier billions of miles away, almost like hearing an echo and drawing the canyon. That long record turned out to be gold. On June 10, 2020, results described by NASA and Princeton, published in the Astrophysical Journal supplements, showed what happens over a full 11-year solar cycle. When the solar wind gusts harder, the heliosphere inflates like a balloon. When the wind calms, the bubble contracts. Those changes do not show up instantly at the edge. There is a delay. The response in the returning particles echoed 2 to 3 years later because the signal had to travel out and back. This matters for the heating story because it tells us the edge is not fixed. It breathes, it pulses, it reacts to what the sun did years earlier. In late 2014, spacecraft near Earth detected a surprise increase in solar wind pressure of about 50%. That was the sun taking a deeper breath. 2 years later, IBEX saw the effect flare in the heliosheath. About 2 years after that, the change spread farther over the front and over the poles of the heliosphere. Cause and effect, but stretched across years and billions of miles. Justina Sokol, a scientist on the Princeton team, and Jamie Saleh, another Princeton researcher, helped describe how this long wait let the shape emerge. Time and particles painted the distances for us. That line sticks with me because it turns the edge of the solar system from an invisible idea into something almost touchable. Not touchable by hand, of course, touchable by patience, by letting enough years pile up for the picture to reveal itself. And what picture did it reveal? Not a perfect sphere, not a neat globe around the planets. The IBEX data pointed to an asymmetric shape, more like a comet, with the sun closer to the front and a long tail trailing behind. Scientists had debated whether the heliosphere might be round, or croissant-shaped, or something stranger. The long dataset showed that the bubble's response to solar wind pressure was clearly uneven. That means the bubble itself is uneven. This is the fourth big surprise, and maybe the most human one. The edge of our home in space is not tidy because the universe is not tidy. Scientists expected a simpler shell. They found a distorted, breathing, lopsided structure that swells when the sun sighs. Picture blowing into a soap bubble while a wind from the side keeps pressing on it. You would not get a perfect ball. You would get a shape that keeps remembering the push. There was another riddle hidden inside the IBEX data. In 2009, the mission found a huge bright stripe across the sky, now known as the IBEX ribbon. Scientists knew it had something to do with the interstellar magnetic field outside the heliosphere, but not exactly how it formed. Over time, the data suggested a second, longer process. Some particles likely crossed the heliopause, wandered into interstellar space, lost and regained electrons, then eventually came back. In other words, some of the signal took the long road home. That delay is not a tiny detail. The ribbon seemed to respond roughly 2 years later than the rest of the heliosphere. The expected idea was a direct bounce. The likely reality was a longer loop. Think of calling out in a canyon and hearing not one echo, but another one seconds later from a farther wall you did not even know was there. The edge of the solar system was not merely reflecting the sun. In places, it was processing the message. Who would you send this story to? The friend who loves space, or the one who thinks space is just empty black? Sharing helps the video reach people who would actually enjoy this kind of discovery. Let us zoom back to Voyager, because this is where the human side returns. These craft were not built with today's sleek touchscreens and cloud software. They were built with old parts, old logic, and a kind of stubborn engineering that feels almost handmade by modern standards. Yet on both sides of the heliopause, they kept whispering home. They crossed a region where sunlight is weak, radio signals crawl back over many hours, and every watt of power matters. And still, they gave us the only direct taste of the boundary itself. One reason the heat shocked people is that we often mix up temperature and warmth in the everyday sense. A spark can be hotter than boiling water, but too small to warm your room. The plasma at the edge can be extremely hot because the particles are moving fast, yet so thin that you would not roast there the way you would next to a fire. This is one of those places where nature plays with human intuition. Your skin expects one thing, physics says another. But even after making that correction, the discovery still bites, because the hotter-than-expected plasma suggests something active is happening at the boundary. Compression is one likely clue. Pressure balance is another. In 2020, reporting highlighted by EOS pointed out that the solar wind itself may account for only a small part of the total pressure holding the heliosphere open. High-energy particles contribute more. Even the magnetic field contributes. In short, the bubble around us may be inflated by a team effort, not by one simple outward blast. That changes the emotional shape of the solar system. We like clean causes. The sun blows, the bubble forms, end of story. But the data suggest a negotiation. Solar wind, interstellar gas, magnetic fields, energetic particles, compression on one side, leakiness on another, delayed echoes, a ribbon that takes the scenic route. Every new piece makes the edge feel less like a line and more like a conversation between our star and the galaxy around it. Scientists will tell you they do not fully understand this yet. That is the unresolved pivot in the middle of the story, and it matters. The models had predicted something different. The observed temperature outside the heliopause was higher than many had expected. The compression seems real, but the exact mechanism on both sides is still being worked out. Is it the shape? The local interstellar cloud, sometimes called the local fluff? The pressure of cosmic rays? A mix of all three? The data do not let us pretend the answer is settled. And the local fluff, by the way, is another lovely cosmic insult to your sense of scale. That soft name belongs to a cloud of hot gas through which our solar system is moving. It sounds like lint under a couch. It is not lint. It is the interstellar material that our heliosphere must plow through, shaping a bow wave the way a ship shapes water. So even the outside of our solar system is not empty. It is an environment. It pushes back. The fifth discovery, if we can call it that, is really a correction to a deep feeling many people have. Space is not a simple void. It is structured. It has fields, particles, pressure, fronts, waves, and boundaries that ripple over time. The farther the Voyagers went, the more that lesson hardened into fact. What looked empty from far away turned out to be full of interactions, like hearing silence in a distant room and then, once you step closer, noticing the vent, the pipes, the clock, and the low electrical buzz. Even the timing of the Voyagers tells that story. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed in 2018. That 6-year gap was not because one spacecraft forgot the way. They reached different parts of a changing, moving boundary at different times in the solar cycle. NASA has compared the heliosphere to a lung, expanding and contracting with breath. That image is almost too beautiful for how much hard data sits underneath it, but it works. The sun does not merely shine, it exhales. There is also something haunting about how little direct sampling we have. 2 spacecraft, that is it. 2 needles pushed into the skin of a giant cosmic bubble from one small species on one small planet. Imagine trying to understand Earth's entire ocean by dipping 2 thermometers over 2 railings, years apart, during changing weather. You would learn a lot. You would also know how much you were missing. That is why every confirmed anomaly matters so much here. The old view expected a simple border and a predictable handoff from solar space to interstellar space. The measured reality gave us a perturbed transition region, compressed plasma, aligned magnetic fields, particle leakage, strange cosmic ray behavior, and a bubble whose shape changes with time. Each one alone would be interesting. Together they feel like a rewrite, not of the solar system itself, but of how we imagine where home ends. There is a practical side to this too. The heliosphere helps shield Earth and the other planets from a large share of incoming cosmic radiation. NASA has said Voyager 1 showed that this bubble blocks more than 70% of that radiation. So the edge is not just a dramatic border, it is part of our shelter. If its shape changes, if its pressure balance shifts, if its boundary breathes with the solar cycle, then our local space weather story grows bigger than the space around Earth alone. Would you tell me in the comments which part stays with you most? The heat, the distance, or the fact that 2 old spacecraft found all this? Your comments help me understand which discoveries you want me to dig into next. The farther we go, the more the language itself starts bending. Hot means one thing at a stove and another thing in plasma. Edge means one thing on a table and another thing in a living magnetic bubble. Empty means one thing in a room and another thing between stars. Part of what makes this discovery shocking is not only the numbers, it is the way it exposes how often our everyday words fail in space. But the numbers do matter. A solar wind gust can take about a year to reach the edge. Some neutral particles then take another year to race back toward detectors. The faster signals can complete the round trip in 2 to 3 years. The ribbon can lag roughly 2 more years after that. These are not vague timescales. These are delayed conversations across a border roughly 100 times farther from the Sun than Earth is. A change near us can write its signature across the edge long after our calendars have moved on. And then there is the domestic anchor I cannot stop thinking about. Somewhere in a kitchen, a refrigerator light glows with more familiar meaning to us than the heliopause ever did. You open the door, cold spills out, and your body understands the scene instantly. But at the edge of the Sun's bubble, the situation flips. The dark region we expect to be all cold contains particles moving so fast that the measured temperature climbs far above what models predicted. The universe keeps asking us to separate feeling from fact. John Richardson and other researchers working on Voyager 2's plasma results helped turn that surprise into published evidence. Nature Astronomy was not cheering for a dramatic headline, it was reporting measurements. And measurements are the part that matter most here. Not rumor, not a flashy animation. Actual instruments, on an actual spacecraft, crossing an actual boundary, with actual numbers that refuse to stay inside the expected box. It also helps to remember how hard those measurements were to get. Once Voyager passed beyond the outer planets, it was already working in deep cold and deep darkness. The radio signal grew faint. Commands took hours. Every instrument still running had become precious. And yet that frail voice from the dark was enough to tell us something profound. The solar system is not surrounded by a dead shell. It is wrapped in a living frontier. That frontier is full of contrasts. Inside the heliosphere, the plasma is hotter and more sparse. Outside, it is colder and denser overall. But right at the border, compression and disturbance change the script. One side leaks, one side bunches. One side drapes its magnetic field in a way no one expected. And because Voyager 2 found the outer plasma warmer than expected, the neat, cold outside story had to be revised. Not erased, refined. That is how science grows. Somewhere in all this is a lesson about underdogs, too. The edge of the solar system was once treated like a blank margin. Voyager was once treated like a mission with an ending already baked in. Both outlived those assumptions. The blank margin became a region of active physics. The aging spacecraft became history makers decades after their launch. If you ever needed a reminder that neglected places and old tools can still overturn confident ideas, this is it. And there is one more twist that makes the whole thing feel almost personal. The Sun's outer bubble is the largest thing directly made by our star. It reaches far beyond every planet you learned in school. Yet its distant skin still responds to small changes in the solar wind that began much closer in. A surge near the Sun becomes a swelling at the border years later. Like watching one deep breath slowly lift a blanket across a dark room, the scale difference is almost tender. The sixth surprise, then, is philosophical. We are used to thinking of home as walls that keep the outside out. But our home in space does not work like brick and wood. It works like pressure, motion, and exchange. It is less like a house and more like a campfire's glow pushing into a cold night, shaped by every gust. That means the edge is not the end of a thing. It is the ongoing negotiation that allows the thing to remain itself. That is also why the future matters here. IBEX has already shown how much can be learned by mapping the edge from afar. The next major mission in this story is IMAP, the Interstellar Mapping and Acceleration Probe, also led by David McComas. Its job is to study this boundary in greater detail and with better sensitivity. In simple terms, it will try to turn our rough sketch into a sharper map. Not because maps are pretty, but because the physics at that edge shapes the shield around us. So yes, the solar system's edge is heating up in the sense that scientists confirmed hotter than expected plasma in the boundary region and evidence of compression and change. But the deeper shock is what that heat stands for. It stands for motion where we expected stillness. It stands for complexity where we expected a line. It stands for a cosmic border that acts less like the edge of a plate and more like the skin of a breathing animal. When this story opened, the image was a fever glowing in the coldest dark. That sounded impossible because we were using human instinct to picture a place human instinct has never known. Now the image means something different. The edge is not a contradiction because nature broke its rules. The edge feels contradictory because our first picture was too small. We thought distance from the sun was the whole story. It was only the first chapter. What the Voyagers and IBEX have shown is stranger and better. Far beyond the planets, the sun's influence does not simply fade into black. It presses against the galaxy. It bunches, leaks, shivers, and swells. On August 25, 2012, and again on November 5, 2018, two machines crossed that moving seam and proved that even at the border of interstellar space, the universe is not done surprising us. And the surprise is not just that the numbers were high, it is that the edge keeps a memory. A solar wind surge from years earlier can show up later in the breathing of the heliosphere. A magnetic field outside can line up with one inside. A ribbon can answer late because some particles took the long road through interstellar space. The border behaves less like a finish line and more like a living message board written in particles and time. That should change the way we feel about the dark above us, not because it is suddenly friendly, it is not. It is still vast, silent, and deadly to unprotected life. But it is not blank. It is not empty in the lazy sense. It is full of structure and pressure and memory and motion. The cold dark at the edge of the solar system is not asleep. It is listening, responding, and in some quiet way, glowing. At the start, the idea sounded like exclusion. Few people ever think about the outer boundary of the sun's bubble. By the end, it feels like inclusion. All of us live inside that bubble. All of us are sheltered by part of what it does. And all of us, whether we notice or not, belong to a home whose border is alive and changing in the dark. So when you step outside tonight and feel how simple the sky can look, remember that simplicity is only the view from here. Out there, in the black beyond Pluto, an old spacecraft drifts through a region once dismissed as empty and keeps telling us the truth. The truth is that the edge is warm with motion. The truth is that home does not end with silence. The truth is that even in the coldest dark, the universe is still breathing.